Charles, can you hear us?
I can, yes.
Yes, please, you can then continue because the floor is yours. I've done a quick introduction, but please feel free to make it longer. Thank you.
Okay, great. Well, first of all, thank you for having me here. I've been able to listen to some interesting presentations, interesting panel discussion as well. I'm actually, it's a shame I couldn't be with you, but actually my daughter's got COVID at the moment and I'm having to nurse her, which is it's not something I'm very good at. So hopefully I'll be able to talk to you about something which I'm hopefully a bit better at, i.e. Dynamic cables. And what we're going to talk about is just a little bit about Peritus, because we're quite a small company and people tend not to have heard of us, and then talk through where we are in dynamic cables in terms of the supply chain and in terms of the technology surrounding them, and then talk about some of the risks and some of the lessons that have been learned from the oil and gas sector. Because of course the oil and gas sector has been designing, dynamic risers and cables holding, umbilicals with multiple tubes in it for quite a long time. So there are definitely some lessons to be learned there that are applicable to floating wind as well. Very quickly about Peritus. So Peritus was formed in 2010. So far we've had 0 lost time incidents. So we've got a perfect safety record, basically. It could not be any better. And in terms of some of the work we're doing in renewables at the moment, we're doing quite a lot of cable related stuff. We've done probably half a dozen floating wind projects now, various sort of stages in the early design stages of the cables, and some modelling in terms of modelling the floaters and the cables with Orcaflex and that kind of things. We've also worked on a large number of other offshore wind cable projects, including some kind of stability of the cables and some stakeholder management, crossing designs, all that kind of good stuff. So we've got quite a wide spread of subsea cable related expertise. Okay, so dynamic cables. And I'm going to whistle through this first chunk of stuff because it may be that I'll be teaching some of you to, grandma to suck eggs, some of you who will already know about this kind of thing. But I think there's a few points worth considering, really. So dynamic power cables and static power cables are not the same. And just to be really clear here, in case there's any electrical engineers in the room, we're not talking about dynamic power cables in terms of electrical modulating the electrical power that goes through the cable or playing with that or overloading the cables. We are talking about dynamic cables, i.e. cables subject to movement in the marine environment. Now, obviously, with a cable in the marine environment, there are a lot of influences on that cable. There's the waves, there's the currents, there's the way the actual floater moves. There's interfaces with the cable into the floater, with the cable onto the seabed as well. And that requires a different type of cable design to your generic static cable that we're currently seeing in offshore wind applications. So what we're seeing with the dynamic cables is it's a much more robust design, really. Without going into too much detail, you have a different protective sheath, an HDPE sheath. You'll have probably a larger number of armor wires, generally a minimum of 2 sets of armor wires, which are contra-wound, so you get a torsionally balanced cable. The cores will typically be similar. One thing to note is that the majority of dynamic cables at the moment are what are called a wet design, so they will have no sheath around the insulation, which is important because if you have a 66V cable, 66 kV cable, you can have a wet design and you can allow water to touch the insulation without any issues. When you get up to a higher voltage, say 132 kV, you will need this sheath around the insulation. And there's only been one so far 132 kV dynamic cable installed, which is an oil and gas project. And so at the moment, one of the big areas with dynamic cables, which is an issue, is dynamic export cables. So you will not get a 225 kV dynamic export cable because of this issue between the wet and the dry insulation. The 132 kV cable that was installed, instead of having a lead sheath, which is typical for the insulation, they had a corrugated copper sheath because lead has a very low fatigue life. So there are a number of differences between dynamic and static power cables, and the costs are different as well. Now, we've done some work recently for OREC where we did a lot of stakeholder interaction. We interviewed maybe 70 different companies in the floating wind supply chain, cable makers, ancillary manufacturers, other bits and pieces. And one thing that was very prevalent from that study is that the cost of dynamic cables tend to be underestimated. Because although superficially they look similar to a static cable, actually it's not just the additional cost of materials and bits and pieces, which aren't necessarily massive. It's the cost of having to do more passes through the machines as well. So if you, although an extra layer of armor wire doesn't seem a lot, actually you have to pass the whole cable or the whole length of cable that you're manufacturing through the factory twice. So that ties up the factory for longer, ties up the machines for longer. So the costs associated with a dynamic cable are certainly likely to be significantly more than with a static cable. I know with dynamic cables, there are lots of different ways you can hang one of these things from your floater. From the work that we've done so far, the most probable configurations that we've come across are either a lazy wave or the tethered wave, which you probably can't quite see it, but right down the bottom of the tethered wave, where cable is near to interacting with the seabed, you can, just down here, you can see there's a little tiny tether. So effectively a clamping arrangement that limits the lateral movement of the cable on the seabed. So it just helps with reducing seabed abrasion. And obviously with all of these things, you want to keep your cable configuration as simple as possible. So the fewer buoyancy modules or ballast weights or anything else you have to put on the cable, the better it is. So ideally you will want to simplify your cable configuration as much as you can. Now, the other thing is, when we talk about dynamic cables and when we talk about dynamic cables for floating wind, we're not just talking about the cable, we are talking about the entire cable system. So the cable hang off, if there's a bend stiffener, if there are buoyancy modules, will you need any kind of abrasion resistance at the seabed? You know, how much is the cable going to move? Is the cable actually too light instead of too heavy? And will you have to put some ballast modules down? Will you need connectors? So it's not just a case of, okay, we'll stick a bit of cable here and we'll do some nice fancy modeling. We'll make sure it's okay. But there's a whole rake of other components, other ancillaries that have to be designed for and have to be considered in terms of getting this cable system right. So I guess I just wanted to flag up that when we talk about dynamic cables, it's quite important that the whole system is considered. And also, ideally, not part of this presentation, but you have to consider the dynamic cable system and the mooring system and the way they interact as well. And there's going to be a sweet point to the costs here too, in terms of you can have a very expensive mooring system which limits excursions considerably, and then you have a dynamic cable which doesn't actually have to withstand a great deal of movement from the floater. Or you can have a cheaper mooring system. It allows more excursion of the floater, and you need a more robust cable system that can withstand those movements. So in terms of reducing costs overall, not only should you consider the entire cable system, including the ancillaries, but you also need to consider the mooring system as well, because that will have an effect on the cable system. And I mean, as will the floater. We did some modeling of a floating substation. And actually, the very presence, if we had 10 inter-array cables coming off it, plus a couple of export cables, the very presence of those cables altered the dynamics of the floater. And as the water depth gets deeper, the increased weight of the cables literally hanging off the floater will definitely change the dynamics of that system. So it's something that should be considered, relatively early on in the design. And I guess if you haven't seen them, these are just a few bits and pieces. So there's a bend stiffener, which will need to be designed and specified for the project and for the load you're considering. Buoyancy modules, again, either a custom size or ideally, as the industry goes forward, there'll be a much more standardized type of buoyancy module that you can just say, right, I need 15 number 7s to put on this cable, or whatever it happens to be. And again, ballast modules, also relatively standard, but still needing design work. And then where we are with cables is quite interesting. There is obviously a trend towards increasing voltage as time goes on. And that trend is leveling out at about 66 kV at present. Similar, I mean, it's driven by the fixed wind turbines. However, as I've just said, it's going to be very difficult to get above 66 kV unless there are changes to the cable design or some more work is done on them. One thing which surprises me at the moment, there is not yet a preferred insulation type. There's a number of different types of insulation that's still being used in these cables. So there's been no consolidation on that as yet. And in the ancillaries as well, there are some trends that we can see in terms of the integration of the entire cable protection system to also include the bend stiffeners and other bits and pieces. And as I said, there is a hope that there will become more as the industry develops, and there are more projects, and these projects span a wider range of water depths, that there will be more standardization around the protection systems and around the bend stiffeners and things. There are limitations on them. For instance, there's limitations on the manufacture of PU components, mainly due to the time that it takes for PU to actually start setting. So if you inject it hot, if the component is too large, the bits you injected first will start to cool off before the bits down the other end of the mold have actually got their PU in them. So there are limits on the manufacture of how big some of these items can be at the moment. And I guess the other thing which needs a bit of thinking about is connectors in the system. Firstly, does anyone actually want a connector? And there's good reasons to have them, and there's good reasons not to have them. And then secondly, what type of connector are you going to use? And I think at the moment, the connector manufacturers are waiting to see which way the market goes in terms of for their themselves to invest in the technology and to decide if it's worth it. And I think certainly it's interesting. It'd be an interesting study to see if there is actually a benefit for connectors. I think when offshore wind, floating wind was first mooted, several years ago, the idea was that you'd have these plug and play turbines you could just interchange and move backwards and forwards. But as time has gone on, I think people have realized that actually you don't just want the turbine spare waiting, sitting on the side in case one of yours breaks, because it's just a waste of that asset. And I think the idea is that most of the repairs will be done on site now as well. So it'd be interesting to see what happens with connectors, whether they will become part of the floating wind landscape or not as time goes on. So risk to the cables. I mean, as with any cable, any offshore wind cable, installation is when the cable gets an absolute hammering, or it can do. There's potential for lots of issues with excess strain on the cable, too much bending of it to be crushed, to get damage to the sheath, and those can be managed and reduced with some proper planning, and they can be monitored as well, which doesn't really reduce the risk, but it just helps you know if something has gone wrong with your cable. And once installed, as we said, these cables have a relatively hard life. They will be moving around all the time. So there is each of the components within that cable, the armor layer, the sheathing, whatever else, there is potential for fatigue in those cables. Fatigue either caused by VIV or perhaps more likely direct wave action in this scenario. And there's also potential for cable abrasion, especially down at the seabed. And issues with joints as well. And particularly if there is a plan to have a static section of the cable, or if you like, a dynamic section. Let's say the last 200 meters are dynamic and the rest of it's static. Something like that. There will have to be a join which will potentially have some issues. Just a little bit more about the installation and why it's different to fixed wind cables. So they're certainly bigger and stiffer, if there's twice as much armor wiring on them. The installation, obviously you're pulling the cable from one moving object, i.e. a vessel, into another moving object. And the cable will be moving as well. So the whole dynamic nature of the system and the installation activity needs to be properly understood and properly modeled. And the other area where there's no standardization as yet is the way floating wind cables are installed. Each contractor is going to have their own methods and their own equipment, and each of those needs to be well understood and modeled correctly to determine the actual risk to your cable during that process. And there are, once the cable has gone in, there are, as I say, there's monitoring, which is it's not a mitigation. It's not going to stop things getting damaged, but it might give you an early warning that something's going wrong, that maybe the wave climate is different to that you had expected, or maybe the motion of the floater is different, or the motion of the cable is different. So you can keep a proper eye on actually the fatigue of the cable and how it is in reality compared to your modeling that you've done. The same with visual inspection. I mean, regular visual inspection is going to help you assess any sheath damage or assess any abrasion. I'm currently on the committee of a British standard looking at cables on rocky seabeds. That standard will be out for review in a couple of months. And one of the things we're considering there is abrasion, and just actually how easy is it to spot for a cable on a rocky seabed. Because it will always be underneath the cable on the cable to seabed interface. So actually it's quite difficult to spot. And if you're going to do a visual inspection of a cable, that's going to be done when the weather is relatively good. So actually there's a good chance that your cable will be lying, to a certain degree on the seabed, and you may not actually see the signs of abrasion on the cable itself. So you may have to look at the surrounding seabed for potential views of the cable, lack of marine growth or swept areas and that kind of thing. And then the other two are fairly standard for everything, just making sure you have a decent contractor and there's decent quality assurance all the way through with people who know what they're doing in terms of the cables. And a few things with oil and gas. Now, obviously, there's a lot of oil and gas majors that are moving into the well, the fixed and the floating offshore wind space. And the difference, I think, between floating and fixed is that in fixed wind, there's been a lot of power cable expertise taken initially from the telecom sector. And then as time has gone on over the past 15 years or so, there's been some issues. I mean, a lot of issues with fixed wind cables. But they've been, those lessons have been learnt, and that experience has been taken on board. And so things in terms of cabling in the fixed wind sector are gradually improving. But in terms of dynamic cables, there's very little experience in the floating wind sector. So that experience, really the most easily mappable, transferable experience comes from oil and gas in the terms of the design of a dynamic riser or a dynamic umbilical. And a couple of so there's lessons there in terms of how to model things and the software that should be used and that side of things. But there's a couple of differences as well in terms of actually the costs of the ancillary equipment, because you're not just making one FPSO, you're making 100 turbines. So there certainly needs to be some changes. A leaner supply chain is needed in terms of the ancillary equipment and the design and the manufacture of them. And similarly with the actual floaters themselves, I mean, it seems at the moment like a semi-sub type design for the floating turbine seems to be gathering pace as the most typical one. But certainly it's definitely not an oil and gas structure, and it needs to be treated as something completely different. I was interested in that supply chain discussion earlier, actually, about lessons from the automotive industry. I think that's absolutely right. We are dealing with a different beast here. And here are some of the lessons just in terms of, what should be done in terms of how you model your floating cables, your dynamic cables. You do need a decent set of software, Orcaflex, Ariane. You may need Abacus if you're going to model the cross sections of these tubes as well. And in terms of modeling the currents correctly, and how those currents, especially in deeper water, how those currents vary across the depth of the cable, you'll need something like Shear 7 as well. So these are tried and tested software tools that really should be snapped up from the oil and gas sector and deployed to for dynamic cables in floating wind. Last couple of slides now, just to see these are my own personal thoughts on kind of what we're likely to see and what should happen ideally. So 66 kV cables, great, they seem fine and readily available. We will need dynamic export cables. Dynamic DC, and that's a really interesting question. I used to work for a company that built offshore substations. Now, we built offshore AC and DC substations. We had enough trouble getting a fixed DC substation to be solid enough and have, to limit the movement on those during storm conditions enough so the DC would stay working. So I think a DC floating substation is a long way off. So I think DC cables are probably also perhaps quite a long way off, but something worth considering as we do move further from shore. I think then there will be some work done on the insulation, especially in terms of prediction of failure with the installation, as well as the actual need for a wet design, higher voltage cable, or changes to the sheath design. Cable joints and cable connectors. Is it better to have 2 or 3 kilometers, depending on your inter-array cable length, of all dynamic section, or should there be a joint in it? So there's going to be a cost benefit exercise there looking at that. And do you need that dynamic cable section to be replaceable? Does that joint have to be replaceable? And again, I think industry standards, there will need to be a better set of industry standards for actual dynamic cables for floating wind, which are appropriate to this industry, which are appropriate to this sector, and appropriate to the types of failure that we are likely to get in this sector. So that's it in terms of a presentation. I can see, I think there are some questions up on here.
Absolutely. Thank you very much. I will pick them up. I believe there's also some questions here in the audience. So we can start with the one online. I'm not sure if you had the opportunity to read it.
There's a couple under discuss, and there's one under Q&A as well. I can see on here. So I can read it out.
So I can do that for you. It's easier for me. Whereas the industry got to on our floaters would be disconnected and reconnected in a return to port scenario. This is from Simon Richards.
Yeah, and as far as I'm aware, there's some work done by the Offshore Renewable Energy Catapult quite a long time ago, 4 or 5 years ago, which looked at that, and there's been nothing since. And so I think it depends on a lot of things. It depends on how far away you are from port, for a start, which depends again on the design of your floater. If you have a spar, for instance, as your floater, which is a very deep water, effectively vessel, there aren't going to be many ports you can get that into. So you could end up being a long way away from a port that is able to service your vessel. If you have a semi-sub, you may find you're a lot closer. So one of the ideas that's currently being looked at is potential to have effective, like, offshore maintenance areas where you can tow your spar to somewhere which is still deep but relatively sheltered, where the maintenance is taking place. So during my presentation, I did mention that I think actually a study would be very much worthwhile in terms of looking at the benefit of having connectors. If you are only going to remove your turbine to shore or to your offshore maintenance area sort of once or twice in its life to conduct a major repair, actually, and you're going to have to disconnect the mooring system and everything else. If it takes you an extra 12 hours to connect the cables, is it really a big issue? Because a connector will have a cost. The spares for the connector have a cost. It lowers your reliability because there's another point of failure in the system. So I think there's a lot of things to be considered there before you make a decision about whether connectors are useful in your system or not.
Absolutely. We had another question from Mark Kentis. Which components are in the cable are more prompt to fatigue failure, and what eventual mitigations could be put in place? Yeah,
I mean, and again, that depends on the cable design and on the project and how robustly you are designing the cable as well. I mean, ideally, you would design all of your components to survive for the life of the project. Now, there are parts in the cable, for instance, and it depends on the strain distribution you get within the cable, which depends on the cable design. But typically, you would want the armor wire to fail first. That's how you would be designing your cable. So the armor wire takes the strain, and that is the component that fails first before the conductors go.
I think we have to break up for the lunch, but I still had one question, which was, how could we improve the lifetime of dynamic cables? How do you see that being done from a design perspective?
Yeah, it's a difficult question, and it all comes down to two things. One is the materials you use in the cable. As I say, if you have a lead sheath dry design cable, the lead is going to have a low fatigue life, and that's going to cause you issues. So it's things like choosing the appropriate materials throughout the cable design. So if you change your lead for corrugated copper, for instance, then you have a cable with a longer design life. And the other thing is monitoring and regular inspection of those cables, and just a proper design. Let's spend the money up front getting the design of these things right, getting the design of the ancillaries right as well, rather than some of the issues that have happened on the fixed wind farms is when they spent very little money on the cable design and on the cables. They've almost been an afterthought. And then that has cost them time and money later on offshore. I mean, I can have, for 1 day's worth of vessel time, I can have an engineer sitting in my office for 6 months for the same cost, just doing the design and getting these things right. And getting the engineering right, it also lowers the risk of the project, and it helps with your HSE side of things as well. So I would say get the engineering right.
I fully agree with that one. I would just like to leave another question, which hopefully will not take you much time because it's aligned with what you just said.
I'll be quick.
Off the shelf or tailor-made, what would be your solution for the dynamic cables?
It's going to have to be tailor-made initially for the smaller projects, but I think as time goes on, it's going to become more and more and more off the shelf, especially around the ancillaries for it. So you'll have a tailor-made design, but that may be using standard components. So you'll have you'll use 12 of one standard module or 6 of some other standard module. So the design for each project will be tailor-made, but it will be tailor-made from a different set of blocks.
Okay, understood. I think there's one question from the audience first.
Yeah,
please.
Hi, Trust. Thanks for your presentation. I have a question. How do you see the transmission loss of floating compared to fixed bottom wind farms?
Yeah, I mean, that all depends of distance from shore. And obviously with floating, the massive benefit for it is places like Japan and California, Hawaii, those kind of areas where it gets very deep very quickly. So we've looked at floating wind projects in Japan and in California now, and they're not very far from shore. And actually what we found is in one of those locations worked quite well was to have a floating wind farm with array cables leading to a fixed substation. So effectively the losses then become the same as they would be from a fixed wind farm. It's just a question of siting that fixed substation in a suitable location, a shallow enough area that you can actually get a jacket to work, really.
Thank you very much, Jas, and really appreciate your inputs. Very insightful. Thank you very much.
Yeah, no problem.
So we will then break out for lunch, and we will resume back again at 2:10 Central European Time. Thank you very much, everyone.